Thank you for joining us today. My name is G, and I'm the Research Engagement Manager at Autodesk Technology Center in Boston. And today our speaker is Changliu Liu, Assistant Professor in the Robotics Institute School of Computer Science at Carnegie Mellon University, where she is currently leading the Intelligent Control Lab. In her presentation today, she'll be exploring how generative AI and robotics can automate the journey from design prompts to physical prototypes, reducing human effort in customized product assembly. Using Lego as a testbed, Liu presents an end-to-end pipeline that integrates text to 3D generative design, accounting for physical buildability with a bimanual robotic systems for assembly. And I want to give Brandon Kramer a shout out for introducing us to our speaker. And Changliu, if you're ready, I will hand it over to you.
Well, great. Thanks. Thanks for the great introduction. Yeah, and here today I'm going to share with you our recent work on using generative AI and robotics to enable an automatic design process that turns ideas into reality. Yeah, so we've all done a lot of designs in our either daily life or in work. It's never a linear process turning a high-level idea into a real, a tangible 3D product. It usually involves a lot of different steps. We need to do sketching, need to do prototyping, testing, and redesigning, and some reworking. And yeah, this journey can be back and forth, involving some redesign and modification, which can be time-consuming and preventing us to quickly realize our design ideas and limiting the creativity. And the core question we want to answer is, can we simplify this process? Can we leverage the generative AI and robotics to make this process more efficient for human users? And today we have generative AI, and it can already do a lot of great things in the virtual world. While I was preparing this slide deck, I asked ChatGPT, can you generate a figure for me that shows generative AI can generate images and 3D shapes very easily, and this is the image it generates. Yeah, so they are very powerful. But if the question comes to how can we leverage their capability in the real world, what are the challenges? And essentially, in order to leverage the powerfulness of generative AI in the real world, we need to bake in the consideration of the physical constraints. And there are a variety of physical constraints we'll need to think about. For example, the available resources that we can leverage to build the actual 3D assembly, and also the Newton's law. Certain assembly is not kind of stable. Things may fall apart. We need to bake that into the consideration. And also, finally, generative AI is on the design side. If we want to build the stuff, we also need to account for the builder's dexterity. For example, humans have more dexterous hands to build certain assembly, while robots, if we want to let robots to automate the a building process, we need to take into account what they are capable of or not capable of. Yeah, and today I'm going to share with you our current work in bridging the gap between the current virtual generative design with respect to the a real physical content generation. And we call this pipeline as prompt to product. It consists of two steps. One step is the assembly design step, where we turn the high-level human, like a language description or even sketch, into a physics-aware assembly using primitives like Lego bricks. And then we send this design to the execution module, where we use two robot arms to collaboratively finish the design. Yeah, and this pipeline is very flexible. It can take a variety of human prompts. For example, the first one is a vessel, and that then leads us to the final assembly. And also the second one is the guitar. But in order to realize this pipeline, what are the challenges we solve? We essentially bake in the physical aspects of the problem into the reasoning process of both the design and execution. Yeah, as we mentioned, we need to take into account of the physical resources and the Newton's law. It comes into the physical reasoning as well as the capability of the builder. Yeah, and the most important part actually is this physical law, as it affects both the design side as well as the execution side. You may think that a lot of nowadays robotics research or even like a design research, we can use simulators to give us an estimation of like a physically whether something is realizable. But the challenge is if we come to those complicated assembly, existing simulators cannot properly simulate those contexts, especially those encoded in Lego connections. For example, this is the design we want to realize, and in the simulation, we can simulate the step-by-step building. And then in the reality, we can build that. But let's look at the final like a step. If we connect the final step, then the whole structure collapse. Yeah, but it's very hard for the simulator to predict that. Let's look at this again. I hope this sound can go through, but if not, just watch here. Yeah, once the human releases, the stuff collapse. Then how can we make a good prediction about whether some structure is stable or not? One idea, as the current simulator is not trustworthy, one idea is that we can resort to the finite element method. Yeah, so here are some like a recent work that uses this finite element method to predict the stability of the structure, which is great and capable of simulating like a highly dynamic situation. But problem is this is too slow. If we want to add this as a feedback loop to our design, it will be like the computation time is not acceptable. But leveraging this idea, our insight is that as the Lego bricks or the primitives we're using are highly structured, we can actually use them as a component in the finite element analysis and make the analysis more coarse or like a less fine-grained. So with that, we designed this pipeline that automatically extracts all the forces on each Lego brick and then create a mathematical equation to balance out all the forces in assembly. And if we can kind of cancel out or balance out all the forces, that means this structure is stable. And if we cannot balance out the forces, the structure may collapse. And also using this formulation, we can predict at which point the assembly structure has the largest stress. And we can feed this information back to our design process. For example, this is an example where the human says, okay, I want a chair with a leaning base, and the generative AI generated this design. And then using our analysis, we can say, okay, here, you have too much stress. You need to refine the design. And with this analysis, we actually achieve very minimum sim to real gap. Here is some example where the top layer is our computed stress on each brick. The red ones are like a higher stress, and the black ones are like lower stress. And these ones are within the threshold, then the structure is stable. Yeah, but for the ones on the right, it's more red, meaning that it's over the threshold. And once the human hand releases, the structure actually collapses on the predicted region. Okay, with that, we now have a good and lightweight physical reasoning module that can be embedded into the design as well as into the final assembly, actual execution. Now let's look at how we actually do the design. In order for the design to make sense, we'll first need to have this multimodal interface to take in the human's requirement, and then do this intent inference to infer like what the human actually needs in the like a 3D space. There has been, I guess, a lot of different design pipelines in the context of Lego. For example, the user can provide a menu CAD model or even a text or even an image. And then there's some methods to turn off all of these into like a 3D shapes. With the 3D shapes, we can do the vocalization, and then we can do the Legolization that merges the voxels into Lego bricks, and then finally comes to the Lego assembly. Although this layer design looks good, but the major problem is that it decouples the intent inference with the physical realization, where the intent inferences happen here, taking the human's input, and then we generate the 3D shape. And up to here, the shape represents the intent. And after the intent is fixed, the remainder part is actually to put the Lego bricks to let it mimic the 3D shape. These two things are decoupled, then it's possible to have the situation that we can have a very nice 3D shape, but there's no solution for the stable Legolization, given the available resources, given the inventory, and given the physics law. There has been some approach that add feedback loops to modify the design, but we think this does not solve the fundamental problem. What we propose is to do an integrated design pipeline where we design the shape and assembly integratedly together. And why we can do that in an integrated loop is because the kind of assembly design is essentially a autoregressive or sequential process which can be fit into an autoregressive model. The like a step-by-step building of the bricks can be represented as like a tokenized text. For example, the first brick to put is this 1x1 brick at this location 780, and the second to put is this 1x2 brick at 760. Yeah, with this understanding, then we can actually leverage the expressiveness of current like foundation models, autoregressive models to do that. We can take in the humans like a language inputs or other multimodal input, but we can tokenize that and send those as input to the autoregressive model. And then the model can, start output after getting the humans like input, the model can start to do the output. First output 1, and then this 1 is being appended to the input again, generating the next output, which is X, and append this X again and generate the next output. Yeah, and with these many tokens, 1x1 at 780, this represents the first brick, and it's like a placing location. And with that, we can continually generate this whole sequence of like tokens. And finally, by translating the tokens backwards to the Lego space, we can finalize the whole design. Yeah, and nowadays we have so many foundation models, large language models, it can actually help us do this. And also it has this common knowledge with like a very smart prompt. They can already achieve some minimum amount of design. But the major issue is that they do not intuitively have the physical or 3D physics understanding baked in. And in order for us to achieve the best design, producible design, we will need to kind of inject the knowledge to the models. And here on the slide, there's some like a design without fine tuning, only using the out-of-box llama model. As you can see, it tries to match the shape, for example, sofa. Yeah, but since it does not have the very intuitive physical understanding, there's some collapse of the bricks and also some folding bricks. And both it is also trying to match, but not good. So how do we bake in the physical understanding? We can do two approaches. One is the model fine-tuning, one is the physics-aware inference, and both approach can benefit from our physical reasoning module that we just discussed, this coarse finite element analysis. In order to support the model fine-tuning, we create a gigantic data set called stable text to Lego, which we get shapes from the ShapeNet and then Legolize that, and we make the Legolization stable using our stability analysis tool. Yeah, and then for these meshes, we also try to generate different renderings and then let ChatGPT to label those using text. And then this Lego design and the text is like an input-output pair that will be sent to fine-tune our model. Yeah, but although with fine-tuning, we can already achieve relatively good generation, but there's no guarantee. And in order for us to get the inference time guarantee in the design, we also integrated this inference time physics-aware process, which does the brick-by-brick rejection sampling if some physical constraint is violated. For example, here, we're trying to build a sofa. And the first brick output is this brown one. And then after several steps, we output this new brown one, which everything is good. But then in the next step, there's this red one generated, which collapses with the existing brick. Yeah, and then we do a rejection sampling, asking the model to generate a new token, and then finally we get a valid one. And also in some cases, the model may try to use some bricks that is out of the inventory. We can also do the rejection sampling and then make the new samples within our inventory. Finally, the stability. We check the stability at the end. That is, once we finish all the steps, we check if this final structure is stable. If not, we do rollback, going to the removing all the unstable ones and then redo the sampling. Yeah, we call this as physics-aware rollback. with all of these, our model actually can achieve like a very high success rate in generating the stable features as shown here, or stable designs as shown here. Yeah, and here are some examples that is showing how the models are turning the text input into a design. Yeah, it actually, because we've trained using the ShapeNet with many different categories, it can also take like a different text prompts in generating different categories of the design types. Some numerical results, our method achieves 100% valid design, meaning that no brick is overlapping, and also everything is within the inventory. In terms of the stability score, although there's still like in some cases, even with the rejection sampling, we might not be able to finally get a 100% stable assembly, but the success rate is already the highest compared to all the other methods. It's worth mentioning that with this original llama, it achieves 0% of validity and stability, because it does not have this physical understanding. And in terms of the stress, stress and strain within the design structure, our method achieves the smallest. And the last one is the similarity between the design structure and the target intent described by the language. Our method achieves the highest score. And the generation time is not crazy. It's around 30 seconds. Yeah, and here are some designs and also the final realization. It's worth mentioning this realization has to be done by like human hand. And later we're going to show how robots can do the actual assembly. All right, so that's the design part. The next is once we get the design, how we can make robots realize that and what are the design considerations. The biggest thing we need to think about is the robot embodiment and their skills. For example, manipulating this a very tiny objects is still very challenging. Then how can we make the robots actually manipulate each bricks with high success rate? Our idea is to customize the robot finger. As if you have played with Lego, there are some Lego tools that has two holes on the end that help you do the fine-grained manipulation of the Lego pieces. And we leverage this idea. We designed this tool for the robot, which also has two holes on the end, and then a lever on the other side. So then if we want to kind of attach to a piece, we just press down. And if we want to pull the piece out, we just twist to one direction. And if we want to release the piece, we twist to another direction. And we learn all these parameters just on the hardware, and with very minimal amount of learning, the success rate of pick and place can achieve 100%. Yeah, and this is our first generation finger. It can manipulate the Lego pieces from top, but in some cases we might need manipulation on the from the bottom. Yeah, then we design a new structure which has the knobs on the bottom, so then the bricks can be placed on top of the finger. Yeah, and then in order to increase the success rates, we further injected a camera inside the finger so that we can look at the misalignment through the finger. As you can see here, we can try to align the knobs on top of the Lego brick using the vision camera. Yeah, and this significantly improves the success rate in the final integrated design, integrated assembly manipulation. All right, and with this hardware design, then we build up the software skill libraries for our robots, where we abstracted six atomic skills: pick, place down, place up. That is using the second generation finger, where we can press something from bottom. And then in a lot of cases, during assembly, the robot needs to apply forces on the structure. Then in order to keep everything stable, the other robot can provide support, either to support from the top or support from the bottom to prevent the structure from collapsing. Yeah, and also we also support this transit function to move the bricks around. And with all these atomic skills, we can chain them together to become those meta skills. For example, disassemble is a chain of pick and transit, and assemble is a chain of place down and transit. And we can also do assemble with support if we have two arms, and assemble with press, which we assemble from the bottom and support from the top. And also we can do handover. Yeah, that is one robot picks up piece and then hands over to another robot, then the other robot can do the assemble from the bottom. Okay, with all of these, then the actual manipulation problem becomes how we chain those skills together to realize the final assembly. And it's worth mentioning that all the atomic skills are learnable. We just create essentially text labels of them so that when we do the high-level planning, we know which skill corresponds to which policy. And if we want to achieve a long-term task, which skill needs to be chained together. And finally, with all of these, we can do the final multi-robot design for the execution and assembly. But in this whole loop, we still need multiple layers because the physical reasoning gives us the stability of the structure only, and then we need to reason, okay, what is the sequence to put together the whole structure, and which robot should do which task at which time. And then finally, how can we monitor that the robot is doing the actual thing in the actual execution? The first is the assembly reasoning. Although we have injected the physical reasoning to the LEGO GPT that we introduced, but the final assembly design is stable, but the sequence that LEGO GPT generated may not always be stable, and this is something we're trying to improve. But for now, given that sequence may not be always feasible, we then need to do an assembly reasoning step to tweak the sequence a little bit so that every step is reasonable and physically valid. And in order to do that, we do just command assembly by disassembly search. And then during the search, in order for it to obey the physical rules, we will use the action masking. For example, from the final product, we do backward disassembly. The left one is invalid as this is like this will create an unstable structure. The right one is also invalid, although the final structure is valid, but this brick is very hard to be removed by the robot, given our finger design. And then finally, with all of these, we can do very efficient online search for the assembly sequence. Yeah, and this assembly sequence takes in both the robot setup, the assembly design, and the manipulation skill, which can generalize to a variety of situations. Yeah, and also during assembly reasoning, we can also search for the points where the robot can apply contact. Yeah, for example, here, the transparent bricks, this orange one and the blue one are the contact points for the two robots. And if we just use one robot, then we'll generate a different disassembly plan. And in some cases, we may regard certain assembly not buildable by a single robot, and then the system may request additional robot arm in order to provide support during the assembly process. Yeah. Once we do this assembly reasoning and understand the contact points of the robots, the next is to translate this contact motion back to the full robot arm motion. Yeah, and in our case, we consider this bimanual manipulation. The challenge is that how to balance the safety aspects during this very confined manipulation and the efficiency aspects, especially when we have a lot of components to assemble. On the left is a real collision that we experienced during our assembly. As you can see, as the two robots collapse into each other, it creates an earthquake on the table. Okay, yeah, and to address this motion planning problem of the robot arm, our strategy is we first find a safe but coarse motion plan, and then try to compress this motion plan to the limit such that it's still safe, but with the minimum make span, that is the minimum execution time. Yeah, so the pipeline is as shown here. Given the assembly sequence that we figure out doing assembly reasoning, we assign different assembly steps into different robots. Yeah, for example, assembly of the brick K is assigned to the green robot. Assembly of the brick K+1 is assigned to this blue robot. Yeah, and then we can, if there's assembly with support, then we can also do the proper assignment. Yeah, and on the time scale, these are like kind of decoupled. First do the assembly of brick K and then do the assembly of the K+1. But actually, a lot of the motion can be kind of doing in a parallel way. Yeah, and how we can kind of encode which motion can be done in a parallel way and which motion cannot. We post-processing this sequential task graph and introduce two types of dependencies. First dependency is the task dependency. That is, brick K+1 should be placed down after the previous brick K. And then the second type of dependency is the motion dependency. That is, for the trajectories of both robots, if there's collision, then one robot should yield the other robot. Yeah, and this corresponds to the green arrows as shown here, while the task dependency corresponds to the gray arrows. And with all these dependencies, then we can compress the whole trajectory down and also execute simultaneously. If, for example, if the green robot has finished this point, then the blue robot can go all the way to the a subsequent task. And with all of that, we can make the bimanual assembly very efficient and safe. Here's a simple comparison. If we do not do this like a final compressed and a parallel execution and only do the sequential execution, it is safe because the other robot is always waiting while the robot is kind of doing the task. Yeah, but this takes too long. And if we have multiple bricks, this will the computation time and the execution time is unacceptable. But with our approach that compress the execution, the robots can simultaneously grasp the objects and then do the assembly. Although one robot waits the other due to the task constraint, but this can be done very efficiently. And with this pipeline, we can actually assemble a lot of the designs that is generated by our LEGO GPT. Yeah, here's some example. The cliff shown here and the branched stairs. And also some very complicated structures can now be built. For example, this S, it is quite unstable because it has this like a hanging structure. But with the dual arm collaboration, it now can be built with good efficiency. All right, with that, I would like to conclude my talk. So this talk is to show you how we can actually leverage generative AI and the robotics to automate the pipeline from the idea to the reality. And we believe this introduced a new mode for human AI and human robot collaboration where the human creativity is not kind of suppressed, but supported. And also the realization of their creative ideas can be much faster than before. And we believe this will have like a wide applications in education, entertainment, and maybe in the manufacturing world as well. And we hope that in the future that both generative AI and robotics can work collaboratively with humans. And also in our own pipeline, we are trying to inject human collaboration in different ways. In the design phase, we can let human do the fine-grained adjustments. In the execution phase, we can let the human build the structure together with the robot. And we believe this will open up whole lots of opportunities in the future. And I would like to acknowledge the collaborators and students who contributed to this project. And also this project is supported by CMU's Manufacturing Future Institute, which is made available by a generous donation from Carnegie Mellon Foundation. Thank you.
Thank you so much. And I would love to open up for questions if there are any from the audience. Please feel free to come off mute. Changliu, are you familiar with the some of the other work that's happening across different institutions that you're also drawing from in your research group? Some of the things that you mentioned reminded me a little bit of like MIT's Dream Fusion, and I know Stanford also has a very similar work, but it lacks a lot of the like physical like grounding that you show in your research. I'm just curious how a lot of these academic research kind of come together, or if you're drawing from any of those. Can you speak a little bit more about that?
Yeah, that's a great question. We did start this project from Dream Fusion. Yeah, we were thinking about like using Dream Fusion to generate a 3D shape and then do the localization and then do the assembly. And find this is really hard, although in the beginning we try to add feedback loops to the Dream Fusion to guide its design, but find this is not very scalable. And also that motivates us to look into a lightweight physical reasoning module. Yeah,
Mm.
and after we get a physical reasoning module, then we think about, okay, why not we just do this design, like a prompt to design as a like integrated pipeline instead of relying on like the intermediate shape level.
Thank you. And I know Desmond has a raised hand. Please feel free to ask away.
Hey there. Thanks for sharing this. It's a really interesting presentation. The question I had was around the interface, right? Like this is awesome that it can be done. You mentioned some implications for manufacturing or even education. How are you thinking about an interface that would be simple enough for, young people, children, elementary school age people to be able to engage with this type of product?
Yeah, that's a great question. So actually we're currently exploring this like idea in a more commercialized domain. So our idea is that first, this whole pipeline can be used to teach young kids about the capability of generative AI and the robotics. Yeah, so then and also a lot of like a teaching platform, we need to kind of predefine the content. But our pipeline, you don't need to predefine the content. The content can be generated by the user. User say, okay, today teach me how to build a guitar. And then the generative AI do the design, and then the like maybe some low cost robots, for example, some low cost tabletop bimanual manipulator can help the children do that. This is one type of thing. And second is this can, if it's done like properly, this can really help young kids in realizing their design ideas when they want to kind of participate in some like a competition or something. I have a young kid at home. He always turns to me, Mommy, how can I build this thing? How can I build that thing? Yeah, and I will need to kind of digest what he needs and then try to maybe use ChatGPT to search how to build that and then try to use my hands to do that. But with this whole pipeline, we can kind of shorten this process quite a bit. And the kids can have like a faster feedbacks using these tools and gradually improve their design in the process and also improve their own capability.
Got it. Thank you.
Mhm.
Yeah, I also have a question. Changliu, nice to see you again. I was curious about if you and team had thought about other, other building blocks that you use. So far you've used Legos and they offer a lot of creativity and ability and flexibility. But when you start to branch maybe more into manufacturing, the components that you would use, of course, have more restrictions. So I'm curious how you've discussed or thought about entering like transitioning your experiments into other applications that would require building things with parts that have more nuance and facets to them compared to the Legos.
Yeah, this is also something that we're currently considering. As the final goal is to make this pipeline able to handle like a wide variety of inventories that go beyond Lego. And the major challenge comes from the manipulation side, I would say. The design side, if we change different primitives as well as we can like properly encode their geometry and the like a contact property, it's not a huge problem. Yeah, but manipulating those complicated parts is still a challenge. But the advantage of our pipeline is that we've already decoupled a lot of the manipulation parts from the like a task level planning to the fine-grained manipulation. And if we can properly define the inventory, we can then develop targeted fingers as well as skills to handle those new parts. And this is also one of the current efforts in expanding the skill library and the skill graph. Yeah, we're trying to also look at different Legos, for example, Lego mechanics, the type of like a fine grain insertion, as well as some like a NIST benchmarks, like a NIST file box, and enable our current like manipulation skills to handle those. Then once this is enabled, then we can leverage our planning pipeline as well as design pipeline to chain everything together.
Yeah, makes sense. I was just doing a quick Google search on the Lego mechanic or Lego Technic, and all like you're using the standard bricks now, but I think even within Lego, there's probably a way to help explain how this would translate into other industries just through the vast inventory that Lego has to offer with a lot of their complex pieces and bricks. So very cool.
Yeah, thank you.
Any other questions or thoughts? Otherwise, I want to thank our speaker for her great presentation today. And thank you, Brandon, for introducing us to Changliu Liu Lab's work, and everyone else for joining the call. Thank you.
Thank you.
Thanks a lot. Take care. Bye.
Bye.